Hello everyone, I'm Salah Din Hetarani, Field Application Engineer at OneSpin Solutions Company. So briefly, what does OneSpin do, or what is OneSpin? OneSpin is a mid-size EDA company that develops IC integrity formal verification solutions to develop secure, reliable, trusted integrated circuits. So today we are going to talk about one of the apps that OneSpin developed to formally verify RISC-V based cores. So why RISC-V cores are, or RISC-V in general, is so popular? This is due to its highly configurable open source instruction set architecture that supports many variations of microarchitecture choices. So it's used in critical application domains such as autonomous vehicles, such as aerospace and military and so on. And for these kind of applications, basically security and trust requirements are so high. So either if you are an IP vendor that is developing your cores based on RISC-V, or you are a company that is building its own RISC-V core from scratch, you need to do verification. And this process is not easy, which comes due to the fact that RISC-V has many optional instructions and features that are provided for the user, as well as the microarchitecture variety that it supports in terms of the pipeline depth and the execution of instructions. Is it in order, out of order? And on top of that, there's a provision for custom extensions that users could add as well. So this makes it really complex and hard to verify. So the conventional ways of doing such verification is to use simulation. But simulation itself is not enough. Now, why I'm saying that simulation itself is not enough? Because simulation is not exhaustive. Even if you spend months, let's say, of setting the environment, verification environment, and running the simulation on each instance, still there would be bugs and hardware trojans that you won't be able to detect. And on top of that, you won't be having unbounded formal proofs. So, as I said, OneSpin has developed an app that formally verifies RISC-V based cores and provides full proof of these cores to have no bugs at all, and as well as ensuring that the implementation is compliant with the standard itself, with the ESA or privileged ESA. Okay? And this has been proven on two 32-bit and 64-bit cores, open source and commercial cores, actually, as we will see in the next slides, with setup time of less than a week and proof time of 2 hours sequential runtime. So if you have, let's say, many cores, you run the properties or assertions that you get on many cores, you could obtain the results with less than 15 minutes. So the general flow of the OneSpin RISC-V formal verification is as the following. We have RISC-V core developed in RTL. Basically, based on this design, we extract automatically information telling us what were the design choices regarding the extensions used. We do some configuration, setting the I/O interface, and figuring out what is the pipeline depth. Now, after doing this configuration, and based on our internal formalization of the instruction set architecture itself that is developed in System Verilog, we generate formal model that is later compared to the RTL implementation and checked using OneSpin 360 formal verification engines. Worth to mention that FloatingPoint Extensions instructions are also verified and included in the app. All these instructions are based on the IEEE 754 standard, And by nature, this standard is complex to implement and it's hard to verify. historically. So OneSpin developed many approaches to tackle this complexity, and we already have paper that was presented in DivvyCon US 2018 in cooperation with Xilinx about providing complete proof of 32-bit formal floating point multiplication. So, as I mentioned, one of the cores that the app was tested for, let's say, or used for, was the Rocket core. This core is 64-bit, 5 stages pipeline with out-of-order completion. And we found many issues. Here's just a list of some of them. As an example, for out-of-order completion instructions was the division operation, that its result wasn't written to the register file. Another example was to find undocumented non-standard instruction, which was seize instruction, which means that this is a hardware Trojan that makes the core vulnerable for unintended behavior if someone wants to do whatever they want to do with. So another example was as well to find undocumented non-standard CSR, and as an example about exception violation, where exception was supposed to be thrown but the core didn't, was to execute return from debug instruction outside the debug mode. Now another example of 32-bit core was the RISC-V core that is part of the Pulpino, or used by the Pulpino platform, that is part of the PULP project that is developed by ETH Zurich and the University of Bologna. Here we found 13 issues. All of them were reported to the developers. Some of them got fixed, and the rest are still under investigation. So I would like to go through only 2 out of the 13. As an example, there was wrong physical memory computation where PMPs were searched beyond the first match in order to be sure that there is a legal access. Another example of floating point extension related was that there was wrong value or wrong rounding mode calculated. So the updates for the rounding mode weren't visible for next instructions, and we figured out then that this issue is caused because of stalling problem. So for such scenario, there was supposed to be stall, but it wasn't the case, and thus the update of this rounding mode register wasn't visible for the next instructions. Now beyond the core, OneSpin has plenty of formal automated apps that could be leveraged to check the whole RISC-V system-on-chip design. Among which we could talk about FSM reachability analysis or dead code analysis. So if you are interested in optimizing your code or your design regarding area, figuring out which parts of the code would never ever be executed in any execution run, then you could run these checks basically and figure out that, yeah, these parts of code would never be reachable. Same for FSMs. You would know which states are reachable or not, and you would know which states, let's say, if the design would enter 2 would never get out. So you have deadlock case that you would never be able to get out from. Another app could be interesting is the connectivity checking app. If you have a design that has very deep hierarchy, and for example, you need to check that your clock is distributed to all modules and sub-modules across the hierarchy, then you could use this app to check that all your signals are connected. Last but not least, the protocol compliance app could be used if you have an interface that is based on certain bus protocol. So if you want to be sure that your interface is implemented in a way that is compliant with the standard, then you could use as well this app just to be sure that there are no violations. As an example of system on chip that was verified using OneSpin is the Pulpino itself that uses the RISC core that we've just talked about. So it has, as a system on chip, it has a rich set of peripherals, and we found 3 issues in this system on chip. One of them was to have unique case statement violation that leads to unexpected instruction decode, which is a security problem, because it also puts the core in a vulnerable way where it could be exploited to do a scenario that you won't expect or you don't want. Another example was to find wrong calculation of floating point addition in the case of adding -0 plus -0. And last issue was about bus protocol violation regarding the APP interface. So to summarize, we talked about how RISC-V cores can be verified exhaustively to be sure that there are no bugs and no unintended, let's say, behavior that you don't want to be executed is there. Beyond the core, figuring out security or trust issues and absence of hardware Trojans. We saw how this have been applied to multiple RISC-V cores, and how could we combine the already existing formal automated apps with this app to verify the whole system on chips. And finally, all these results obtained using OneSpin suite of verification tools. So if you have any questions or you would like to talk more, please just do it. Thank you.